Hey, welcome back. In this video, we're going to talk about the calculus of polar curves. We're going to attack the area bounded by polar curves first. Then we're going to talk about the arc length of polar curves. And finally, we'll talk about finding the slopes of polar curves. First up, to find the area bounded by a polar curve, we first need to revisit a concept that you've definitely seen before, and it's not really that difficult, but finding the area of a sector. So in this case right here, we know the area of a full circle is pi r squared, but we don't want a full circle. What we want is this little wedge piece right here taken out of a full circle. And how we'll describe this is, so theta is the angle created by this wedge right here. So just the angle right here decides how wide this is, and then r is obviously our radius. What we do simply to find the area of a sector is that we simply take the area of the entire circle that would be described if theta was as big as possible. So if theta was 360 degrees or 2 pi, that would describe the whole circle. So we take the area of the full circle and we're going to multiply it by the percentage or the fraction of the circle that we have. And so in this case, the whole thing would be pi r squared, as we know. And so we want to figure out, well, what percent or what fraction does this represent of the entire circle? Well, we know the entire circle in radians, the theta would be 2 pi. And so that fractional amount that we have of a full circle is theta divided by 2 pi. Would be taking the full circle. So if we had the full circle, we'd have pi r squared would be the entire area. But we want is a fractional amount. We can easily determine, so since our sector is defined by this angle right here, what we do to find what fractional amount of the full circle we have, envisioning a full circle, would be by taking theta divided by the angle for a full circle, which would be 2 pi. And again, quickly, like for instance, if theta was equal to pi, meaning we had this angle that was pi, we'd have a half circle right there. This theta, if theta was pi, it'd be pi divided by 2 pi. The pi's would cancel. I'd get 1/2, which is what I'd want. I'd want 1/2 of the entire area of the circle. And just to clean things up here real fast, we will cancel these pi's between those right here. So our formula for the area of a sector is 1/2, because of this division by 2, r squared theta. To me, super interesting about this formula right here, when we write this in terms of radians, you don't see a pi here. So we're finding this area of something that's proportion of a circle, but it doesn't involve pi in any way. Though you'll notice if your theta value was 2 pi, again, meaning you want the area of the entire circle, when you put a 2 pi here, the 2 and the 1/2 would cancel, and you'd be left with just a pi or pi r squared for the area of a full circle. But anyways, that's how we find the area of a sector when our angle is determined in radians. All right, now to develop the technique for finding the area of a polar curve, we're going to do exactly the same treatment that we've done previously many times to employ integration by breaking these up into small intervals. The really interesting change here is our independent and dependent variables and how that interval will look. Specifically right here, we're thinking about our radius in terms of theta. So as we change the angle, the radius changes, but the independent variable is that change in the angle. So when we do intervals on this, so subintervals of this theta from A to B, what we'll get are these intervals that look like this. So coming from here, we have these angles that are cutting these little intervals. These are the n intervals that we're describing. The really important difference when we do this is that we don't have these rectangles. So we're not going to find the area of rectangles, but what each of these are small little sectors. So what we're going to do is the same treatment we've done before with these sub-intervals that we're creating over our interval that our independent variable is being described, but we're not going to be finding the areas of rectangles. We're going to be finding the areas of these sectors. So then looking at our represented interval, again, this interval is a sector, not a rectangle, and it's defined here by these angles of theta sub I minus 1 and theta sub I. This is the ith interval being described right here. Importantly is this delta theta is the change in these two angles. So this is again a little bit different than we've seen before. It's not this width of the interval, it's the angle of this interval. So again, then the setup is we're splitting this interval into n subintervals. We have the ith interval described here. We know that interval now is not a rectangle, it's instead a sector. And so if we want to describe the area of the ith interval sector, what we get is exactly that equation. So 1/2, and then r squared. So r in this case changes with the theta value. So we'll just take a representative point, sample point on the ith interval. And so this will be r sub theta I star. Again, that's, the star is just saying any of those points on that interval is just fine for representing the radius of that interval. We are squaring this, that's important, times the angle, the size of the angle, but we talked about this for this representative sector. The size of the angle here is just this change in the theta values, the change in the angle, this delta theta. And then we don't want just the area of one of these. To find the entire area, what we're going to do is let the number of these subintervals go to infinity. We're going to sum together all of those areas, and we have this, which is a beautiful Riemann sum. And then we know that applying this limit sum will give us an exact area for the area under this curve for theta values from A to B. Thus, and you know that the punchline at this point, we have this limit sum applied to this expression that has this delta. As n goes to infinity, this gets an infinitesimally small. We now have an integral. This integral is from the values from A to B of 1/2. Oh, and this is r squared. I'm sorry, I didn't write it here. R squared. So 1/2 r squared. Again, r is a function of theta, but in this formula, we'll just write this as r squared to make our lives a little bit easier. R squared, and then this delta theta becomes the differential of theta, or d theta. All right, so here in our first example, we're trying to find the area bounded by this curve, r equals 5 sine of 2 theta. By the way, what this is one of these roses that has 4 petals, because it's double this even number right here. And then the maximum length or span of those petals is this 5 right here. But we're actually not looking at the full rose shape. We're just looking at a fourth of it as theta goes from 0 to pi over 2. So straightforward, what we're going to do is just apply this formula right here. Again, this is R. These are my A and B values. So I have that the area of this is the integral from 0 to pi over 2 of the 1/2 that I always have right here. R squared, so R squared is this right here, 5 sine of 2 theta squared d theta. And then first of all here, just to clean things up a little bit, I'll apply this exponent of 2 to both of these factors. I get a 25 sine squared of 2 theta. And just to pull out my constants, I'm going to take this 1/2 and that factor of 25 I get and pull it on the outside. So this will be 25 halves, and so we're still going from 0 to pi over 2, and now we have the sine squared of 2 theta. And again, thank goodness that we practice these powers of these trig functions, right? They do come up a lot. What I'm going to use is the power reducing formula for sine squared here. So I'm just going to rewrite this. So 25 halves from 0 to pi over 2. So this becomes 1/2 times 1 minus the cosine of, it's 2 theta or 2x, but it's always double what I had. So I had 2 theta, and so now it becomes 4 theta d theta. Just going to clean this up a little bit. I'll pull this factor of 1/2 out again because it's simply a constant. So I pulled out that 1/2. Now I can actually integrate. What I could do right now is do a u substitution for this 4 theta right here. But again, I like to do this if I have just a linear expression inside of a function. I just kind of do this thinking of anti-chain rule. where when I turn this is going to turn it into a sine. When I integrate, I'm going to divide it by 1/4. And so what I'll get here is I'll have 25/4 integrating these terms. This just becomes theta. So the integral of 1 is just theta. Then this right here is sine, or 1/4 the sine of 4 theta. And we're evaluating 0 to pi over 2. All right, and then plugging in my interval values and evaluating. So again, I have this 25/4 on the outside and theta. So I plug in pi over 2 here. And then I get minus 1/4 sine of 4 times pi over 2. And so that's my first term. And then minus plugging in 0. Actually, I can see right away 0. I'm not even going to write it all out. 0 doesn't do anything because I get a 0 here minus the sine of 4 times 0, but that'd be just the sine of 0. And so that term just becomes 0. And then evaluating this is 4 times pi over 2, which would be 2 pi. So the sine of 2 pi is 0. So actually this term goes to 0. So the only term that actually offers anything interesting was when I plugged pi over 2 in right here. So I get 25/4 times pi over 2, which would equal 25 pi over 8. So again, something that you would expect when doing these, especially because of this r squared right here, is you're going to have to employ these tricks that we had for attacking powers of sine and cosine functions. Importantly, again, what I used right here was the power reducing formula. So for sine squared, it's 1/2 times 1 minus the cosine. And importantly, again, to say is this right here, the argument of the cosine or this function expression inside the cosine is always just twice what it was. So if I had sine squared of theta, I would get the cosine of 2 theta here. But since I already had a 2 theta, I get a 4 theta. Anyways, and the other trick I used, and that will happen when you use this power reducing formula, is from here to here, I could do a u substitution where u equals 4 theta. And I would get this factor of 1/2 that ends up coming out. But for me, it's a lot quicker, and I'm used to doing this at this point. Not saying you have to, but I'm just going to integrate this, and then I'm going to divide by that factor of 1/4. Again, that's the idea of thinking the anti-chain rule, that if I did differentiate from here to here, I would have a factor of 4 that comes out. This 1/4 would cancel that factor of 4. All right, now it's time for a little bit more fun. And in this case right here, we're being asked to find the area that lies between two curves, but specifically the area that lies inside of the circle described by r minus the sine of theta, but outside of the limacon that's r equals 2 minus sine of theta. So here's my beautiful picture here representing these two figures right here. Again, r equals 3 minus sine of theta is a circle. It's sitting here. It's basically sitting on this pole or the origin point right here. It has a diameter of 3. And we have this limacon. This isn't one of these cool ones because it doesn't have the little blip right there, but that actually will make it a little bit easier for us. But what we're looking for, as described in this problem, is this area here. So it's inside of this circle, but outside of this limacon. So here's going to be our general attack strategy. And these can be quite a bit more complicated than just looking at two functions on the XY plane. But what we're going to do is this. First and foremost, we're going to identify values for these intersection points right here. This is going to give us a range of values for theta. Importantly, actually, when you solve for when these points intersect, because any point on the polar plane can be described by an infinite number of points, what we're just going to be looking for is just one solution for this range right here, starting from that point to that point. Because what we're going to do is we want to find the area first, looking at these angles right here. So we're going to look on this limacon right here. We're going to calculate this little area right here inside of here. So that will be the area described integrating this over those angles right there. And then what we're going to do is do the same treatment for the circle on, not the whole circle, so not the area including this stuff. This isn't going to be calculated at all, but we're going to calculate the area of the circle between those two intersection angles right there. But then we're going to subtract out this area right here from the circle on that same range, which will end up giving us that area. So again, just to give a little graphical representation of what we're going to do, we're going to find the area of the circle, but a part of it that looks something like that right there. And then we're going to find this area described by this limacon right here between these angles right here. So we're going to find this area, and then we're going to subtract away that area from the area of that most of the circle. All right, first up, to find those intersection points for those polar curves, what we're going to do are set these equal to each other. So we have 3 sine of theta equals 2 minus sine of theta. Add sine of theta to both sides to give me 4 sine of theta equals 2. Divide by 2, so we get that the sine of theta equals 1/2. And again here, if we use the sine inverse function, we'll get one solution, but we know we're looking for two solutions, and there are two places on 0 to 2 pi where this is true. But just to look right here and applying the sine inverse, but this is a known value right here. The sine of theta is 1/2 when theta equals pi over 6. So that would be this point right here. And then this point right here is when theta equals 5 pi over 6. All right, and again, we're trying to find this area right here. And the argument was, what I'm first going to do is find the area of this circle on this range of theta values that will describe this. Not these little bits right here, but everything described here and cut off by these angles. And then I'm going to subtract away the area of the limacon over that same range of theta values. So what that will look like here is that my area equals the area of the circle on that, domain of theta values. So 5 pi over 6. This is 1/2 r squared. So that's sine of theta squared d theta. And then we're going to subtract away the area of that limacon on the same domain or same interval of theta values is 1/2 times 2 minus sine of theta squared d theta. All right, that's my setup. And as you can see, there's going to be a bit going on here. I have two integrals, but for me, just to make my mind a little bit easier, I'm just going to combine these. I can do this because they're definite integrals, integrating over the same value on the same bounds right here. So I'm going to put these together. I'm going to do a couple things just to keep this from being chaos. I'm going to put these together, so it ends up just going to be this minus this in one integral. I'm going to factor out the 1/2. And just to save me a little bit of board space and time, I'm also going to square this term, so apply that exponent there, and then FOIL out and squaring these two terms right here together too, or multiplying that out. All right, so there I have it. Again, this 9 sine squared just comes from squaring this right here. This jazz just comes from multiplying out this binomial that got squared. And then the 1/2 is the same 1/2 I had in both that I factored out. What I'm going to do now is I'm going to distribute this negative through. The only really interesting that's going to happen is there'll be a minus sine squared. I have 9 of these sine squared, so I'm going to get 8 sine squareds. So let's see what we have here. So we're going to have this 1/2. We're still from pi over 6 to 5 pi over 6. So that minus that will give me now 8 sine squared of theta. And then now I have a plus 4 sine of theta. And then minus 4. And we are d theta. So after all of that jazz, it's not too bad. The only term that kind of sucks is this first one. I'm now going to apply the power reducing formula, just like we just did in the last example, to this. I'm going to clean things up and write it over there so we can attack the next steps. And so again there, all I've done was applied the power reducing formula to the sine squared of theta right here. That 1/2 on the outside, by the way, to make it clear, there's 1/2 times this, but that 1/2 got multiplied by the 8. Just going to clean up one last time, then I actually get to integrate here. I'm going to distribute this 4 through. I'm going to get a positive 4 minus 4 cosine of 2 theta. But importantly, that positive 4 and this negative 4 are going to cancel out. So what do we got here? We have the area equals 1/2 the integral from pi over 6 to 5 pi over 6. So the 4's get canceled out. But this does become minus 4 cosine of 2 theta plus 4 sine of theta, d theta. And just to make my mind a little bit easier when I do this, I'm now going to factor out this factor of 4 right here. And so this will be my last step before I get there. So pull out a 4. And that gets multiplied by the 1/2 right here. So this becomes 2 times the integral of pi over 6, 5 pi over 6. And now we have minus the cosine of 2 theta plus sine of theta d theta. Okay, now we can integrate. These aren't too bad. I'm going to do that little mental U substitution trick right there. And so I get the area is 2 times. The integral of this is going to be negative 1/2 sine of 2 theta. Again, that's that like anti-chain rule factor that comes out right there. The integral of sine, that's always tricky for me for some reason, is negative cosine. Didn't mess it up this time, which is awesome. And we're integrating from 5 pi over 6, or from pi over 6 to 5 pi over 6. So then all I need to do is evaluate by plugging in this right here. So first and foremost, I'll plug in 5 pi over 6 into this. This will give me, so let's just have this here. So this is 1/2 times the sine of 5 pi over 3, because 2 times 5 pi over 6 is 5 pi over 3. If we're at 5 pi over 3, well, the sines of the pi over 3's is root 3 over 2. We're down below the x-axis, so this is going to be negative root 3 over 2. And then we have the cosine of 5 pi over 6. The cosine of 5 pi over 6 is negative root 3 over 2. And so now we have the 5 pi over 6 plugging in the pi over 6 here. So subtracting 1/2 times the sine of pi over 3. So sine of pi over 3, because I'm multiplying that by 2. Sine of pi over 3, well, that's a little bit easier than the other one. It's just root 3 over 2. And then the cosine of pi over 6 is just root 3 over 2. So then just to clean things up quickly here, we have negative 2. Then this becomes negative root 3 over 4 minus root 3 over 2. This term right here will give me negative root 3 over 4, and this is positive root 3 over 2. And excuse me real fast, that's actually a minus because that negative gets distributed right there. Then, let's see, limited space to do what I want to do. What am I going to do? Here's what I'm going to do. I'm going to multiply everything. I'm going to distribute this through 2. I can combine some like terms, but I don't really have the room to do this. I'm going to see if I can do this in one move. I'm going to distribute this negative 2 to all of these terms. When I do this, they all become a positive for 1. This 2 cancels out these 2's, and these right here become halves. I know I'm writing all over this, but again, I don't know what else I can do for space and to get into this. So what I have is all of these square root of 3's, right? So this is a square root of 3, that's a square root of 3. So those together are 2 square root 3's. Well, then I have these half a square root 3's. So those together is another square root 3. Hopefully you followed all that. You can verify that real fast. when I'm adding those all together, what I get is 3 square root 3. Whew. All right, so that was a beautiful problem. I just want to recap what we did right here. And first of all, let's look at a nice Desmos image. I know my graph that I drew at the beginning of this was beautiful, but let's look at Desmos. So again, the idea was we first wanted to find these points of intersection. And when we're doing this, it's important to understand that when we're computing these areas, what we're actually computing. So what we found is point of intersection. And first, we're computing the area of that circle, but not the entire area. Just that shape, it's kind of like a ice cream cone. I was kind of thinking that when I was doing it, right? So we take the circle and make this cut right here. That's what we'll actually calculate with this. But we want to subtract out that same little portion that comes from that lemmason right there. So we take that little ice cream cone shape area that we've calculated with this. We take away that little bit in the bottom that comes from that lemmason right there. And then we've calculated that the area between these two curves that lies inside of the circle, but outside of this lemmason is 3 times the square root of 3.